Welcome to Brain Vision.
Alright, so here we are working on partial derivatives and using them to make approximations. In particular, for this problem, we will be using some data to get a linear approximation of a function. And the definition of a linear approximation is to take the original function at the point AB, add that to the partial derivative with respect to x at AB, multiply it by x minus a, add that to the partial derivative with respect to y, evaluated at AB, and multiplied by y minus b. Okay, and so this means that we can use this to approximate our function f. And so we want to apply these definitions. Now we are given, in this case, our x's and y's, our a's and b's are going to be temperature and humidity. So we have in this case, it's going to be roughly equal to f is equal to our negative 15 degrees Celsius and at 50 kilometers per hour. So it's temperature and wind speed here. All right, so we multiply that by f times the partial derivative at the same values, negative 15 degrees Celsius and 50 miles per hour. And it would be temperature minus 15, which is going to be plus 15. And then add that to the partial derivative of y at negative 15 degrees Celsius and 50 kilometers per hour. Let's see if I can squeeze it in. Y minus, no, can't fit it, but we'll be multiplying that by y minus 50. Okay, and then from the table, here we're using the table, we can actually figure out what f of negative 15 degrees Celsius and 50 kilometers per hour is, and that's going to be equal to negative 29. For the wind chill index. So then to find the partial derivative, I realize I should change these subscripts, right? We're not dealing with x and y, we're dealing with temperature and the wind speed. Actually, we'll call that v. Okay, so we want to take f, partial derivative of f with respect to temperature. And then we can do that by keeping the wind speed at the same and just processing the limit as the temperature changes, right? So this would be equal to the limit of, say, j approaching 0 of our function f at temperature plus j, and we're keeping wind speed the same, minus f of t at 80 over j, right? So this is just the definition of a derivative. But we can plug some of these values in here. We can pick some j's and then take the average. So we're going to say it's going to be approximately equal to f of say negative 15 plus 5 over 50 minus f of negative 15 and 80 over 5. Okay, so this is going to be equal to negative 22 minus negative 29 over 5, which is equal to 1.4. Then we can do the same thing, but we're going to subtract 5 instead. So it's also, the derivative is going to be approximately equal to f of negative 15 minus 5. And 50 for the wind speed minus f of negative 15 and 50 over negative 5, which is equal to negative 35 minus negative 29 over negative 5, which is 1.2. Okay, so then we can say that at this point, so at negative 1550, the partial derivative with respect to t is going to be roughly equal to 1.2 plus 1.4 divided by 2, so that should be 1.3. Then we'll do the same thing to get an estimate for the partial derivative of the wind speed. Okay, so it's going to be roughly equal to, I'm just going to dive into the numbers and ignore the motivation using the definition of a derivative here. So we have f of negative 15, we'll keep that the same, but then we'll change the wind speed by 10, and then subtract our f function at negative 15 and 50. Divide that by 10, so that ends up being equal to negative 30 minus negative 29 over 10 is equal to negative 1/10. And so now we'll do the same thing, but subtract instead. So we're going to get 50 minus 10. Okay, but then the rest of it is going to be identical. Subtract the function at negative 15 degrees and 50 for wind speed. Divided by 10, this is negative 27 minus negative 29 over 10 over negative 10. And this is equal to negative 0.2 or negative 2/10. I realize I wrote that in two different forms, but the actual average is going to be equal to negative 0.1 minus 0.2 over 2. That's equal to negative 0.15. Okay, so now we have all these values, and we can just put it into our equation that we have for linear approximations of temperature and wind speed. So this is equal to negative 29 plus 1.3 times t plus 15 minus 0.15 times our wind speed minus 50, which when you do some algebra is 1.3 t minus 0.15 v minus 2. Okay, so then we're going to use that. We're going to substitute in t is equal to negative 17 degrees Celsius, and that our wind speed is equal to 55 kilometers per hour. And we plug that into our linear approximation. We get that this is equal to 1.3 times negative 17 minus 0.15 times 55 minus 2. So I got that this is approximately equal to negative 32.35 depending on where you round things, you might find that you and everyone you know are getting slightly different answers here, but you should expect a negative 30 something as your solution.